In the second talk, we're going to learn a little bit more about applications and starting to use the platform and devices and FPGA-based SmartNIC, OS4C, and beyond. The presentation is by Scott Smith, who is a fourth-year PhD student also at the University of Illinois, Urbana, Champaign. His research interests include SmartNICs, hardware-software co-design, and compiler architecture. His current research involves developing a more scalable and flexible FPGA-based SmartNIC architecture. He is also passionate about open source and engineering education. He has worked on multiple open source hardware and software projects and designed a summer camp for high school students interested in computer architecture.
Hello, everyone. My name is Scott Smith, and today I'll be presenting on my work, which is FPGA-based SmartNICs, OS4C, and beyond. So this is essentially going to be a summary of a work that I published with a few other students called OS4C, an open source SR-IOV system for SmartNIC-based cloud platforms. The lessons we learned from building this project, and then also what our future directions are as we're building on top of the V80 FPGA. And we'll leverage some of the concepts that Gregory covered too in the previous presentation about partial reconfiguration. So let's get through here. About me, I was just introduced, so I'll get through this really fast. But yeah, I'm a fourth-year PhD student, and I work primarily in the domain of SmartNICs. All right, let's go through the introduction. So first, let's cover exactly kind of what SmartNICs are and why they have been growing in popularity over the last several years. So this is primarily driven by, as many things are, increasing demands on our systems. So in particular, if you look at the network capabilities of your systems, they're growing extremely rapidly. So on this plot here, it shows the single link specification for Ethernet and how it's been increasing in capacity over the last, 40, 50 years. And you can see that these are pretty dramatic jumps in performance. Orders of magnitude jumps, or at least 4x, 10x jumps over over just a few years. And so to just kind of make this a little concrete, if you were to look at two products from AMD and two different FPGAs that have been released over the last few years, if you look in 2021, the LVO U55C is going to be offering you around theoretically up to like 200 gigabit per second network performance. And now if you look at the capabilities of the LVO V80, which has just come out and is available for some researchers, that's now up to 800 gigabit per second. So in just 3 years, you're looking at a very dramatic increase in the maximum network capabilities of just this particular brand of FPGA. So in addition to the fact that these network demands are going up, there's been significant increase in necessity for the network cards themselves that are offering this performance to have more features in order to continue to meet these increasing line rate goals. So if you were to open up just a manual for a full-fledged network card, so for example, the ConnectX 7, and you were to trace through all of the features that they support, you'd have an enormous list of which I've copied a subset here. You're going to look at things like related to RDMA or encryption, different types of statistics gathering, virtualization hardware, and more. And if you were to say open a manual from 10 years ago versus open a manual from a card that's more recent, you'll see that this list keeps getting larger and larger as more and more features are being moved from what was previously in the software stack into hardware. And this is to keep up with those increasing demands that I was showing before, where the throughput keeps going up and up. And in addition to the fact that these network cards are becoming more complex and more powerful, they're also becoming more flexible. So if you were to look at the Microsoft Azure paper that came out a few years ago, in 2018, they expressed a need, essentially, that the network cards that are available to be used in their systems not only have a huge number of functionalities and compute capabilities and throughput capabilities, but also that the exact functionality that they have should be able to be configured by the cloud provider. Essentially, different groups, different cloud providers, different users of these network cards have different functionalities that they might want to support that are not necessarily universal across every possible user of the device. And furthermore, these demands evolve over time as these cards are deployed and used in their systems. So If you were to then only produce cards with fixed functionality, this would require constant respins and production of new custom hardware tailored to specific cloud settings, etc. But if you can instead make it so that the network card itself is programmable and flexible, this would obviate that problem. And so in the paper, they pointed out essentially three key goals that they wanted to facilitate with these more flexible network cards. First is they want to be able to free as many host CPU cores as possible. And this is for multiple reasons. Firstly, host CPU cores might not be able to keep up with the throughput demands that the new network devices are capable of. And second, every host CPU core you have on your server is something you could potentially be selling to a customer. So, right, when you rent a virtual machine or a container or whatever on your cloud, when a user wants to have access to some resource, they're paying for timeshare access to this hardware. And if you have to spend a bunch of your resources instead managing your network or other parts of your infrastructure, then you can't sell those same host CPU cores to your customer. And so by increasing the flexibility and capability of these cards, they're able to maximize the amount of profit they can make from their systems. And the second one, like I said, is you want the flexibility to be able to modify things during deployment or to the specific user. And then third, they need to make sure they're scaling to future Ethernet speeds as these demands keep going up and up and up and don't seem to be stopping anytime soon. So there are a couple different types of network card architectures that facilitate this degree of flexibility and capability. So the first one of these is the on-path SmartNIC, where essentially every single packet follows the same path of the host CPUs generate the traffic. They set up the DMA logic on the FPGA to move the data from the host to the network card, and then all of the packets are passed through basically a pipeline of accelerators or offloads that have some sort of fixed functionality that all packets are passed through. So for example, this could be like encryption or compression, etc. And all packets then would be grabbed from host memory, shoved through those offloads, and then thrown out of the physical interface. An alternative architecture that some SmartNICs have used, or network cards, is that they do the same thing where they set up the DMA, they grab the packets from the host, but they optionally can pass packets through like an on-NIC communication fabric. Some of the most powerful ones right now are using like onboard PCIe. And they essentially grab the packets and then shove them through offloads that are located on like a separate array of maybe ARM cores or specialized hardware blocks. And then once that processing is done, then they send it back over that interconnect and outside of the physical interface. But essentially the goal is similar. They want to be able to have some degree of flexibility and programmable functionality that can do more complex compute than just grab the packet and shove it out of the physical interface. They want to be able to do something else in addition to that. Now, there have been a ton of papers published in the domain of SmartNICs on these programmable, powerful network cards. And these range from profiling. There's a huge number of papers that profile SmartNICs and the pros and cons of the different architectures I just showed you, to things like, okay, how do you support P4, which is a common network programming language, on your SmartNIC, to key value store acceleration, to security, to storage acceleration, etc. And of course, AI. Everyone's into AI right now. There's been also several papers looking at AI acceleration. But the point is that there are a plethora of works in a ton of different domains that are not necessarily well suited to every single possible application that you might want to run on your system. So depending on which things you want to support on your NIC, you want to support these different types of projects. And that's where the flexibility comes in, as opposed to having hardened accelerators for everything. There are also a number of projects that look not at the things you can put on a SmartNIC, but instead on how you should architect one of these network cards. And also, how do you provide a platform for testing your ideas or deploying your ideas in the field. So there are three kind of major open source networking platforms for NIC research or prototyping: Corundum, NetFPGA, and OpenNIC. They all support up to 100 gigabit per second networking in the ideal case, and they follow basically the on-path architecture that I showed before. These are basically FPGA designs you can load onto some FPGA I think all of them, for example, support the U280, and then you could theoretically deploy some custom accelerator offload on top of them. Then there are also some like more state-of-the-art SmartNIC architectures where they're trying to push forward what's possible on SmartNICs and can coming up with more kind of atypical designs to solve some of the feature problems that these earlier ones have that I'll get to in a moment. So like I said, one category is to facilitate the development of other research projects and provide a mechanism for testing ideas. And then the other category is to how to improve SmartNIC architectures and what the current limitations of the current approaches of SmartNIC architectures are. So now I'm going to go through OS4C, which is the paper, an open source SR-IOV system for SmartNIC-based cloud platforms that we published this summer, and kind of what its features are. And then after that, we'll go into its limitations and how our upcoming project will solve some of those. So as many of you are probably aware, when you want to share a hardware device, when you want to share just a typical computer, you need some degree of virtualization to ensure that everyone isn't stepping on other people's toes. So for example, virtual memory, to make sure you're not reading and writing to addresses that another process owns. This is true even for things like PCIe devices. It's a very similar idea. You want to make sure that multiple people can share the device without causing incorrect behavior by accidentally, deleting or overwriting people's packets. You want to make sure that you only are able to read the traffic you're supposed to, so you can't read messages designated for someone else, all that sort of stuff. And that necessitates a degree of virtualization to be placed between the application and the device that they're using. The traditional way is to do this virtualization in software. So if you were to say, look at your basic like networking or OS class, you'd see that basically there are multiple applications. They use a socket interface to generate traffic that they want to go out of the network. The OS is then going to intercept that, pass it through the protocol stack, TCP or UDP or whatever. And then eventually, finally, that'll probably get to the network card and then shoved out of the network. Now, this is well and good. It enables multiple people to share a device. But the problem is that this has a large overhead when you're working at the scales that modern network cards are. So when you're looking at 100, 200, 400 gigabit throughput, this process of intercepting all traffic that the application is generating and then processing it and then finally handing it to the hardware adds an enormous overhead. So there's been a large number of papers that have shown this over the years, but one that was on more recent network cards showed that up to 50% of CPU cycles when you're generating network traffic are spent on just moving the data from user space to kernel space, depending on a couple factors. But essentially, a huge number of the cycles that you're spending generating network traffic are just in the act of virtualizing and handing off from the application to the OS. This problem gets worse once you introduce additional layers of virtualization, because every layer you're building on top of the stack requires, if you do this in software, more levels of intercepting packets and processing them. So in the domain of the cloud, for example, you're going to have multiple virtual machines with multiple applications in each virtual machine, potentially, that are all generating traffic. And if you're virtualizing the applications within the VM and you're virtualizing multiple VMs sharing the same hardware, this adds more and more layers of overhead to your software stack, which can dramatically reduce your performance. If you look on the figure on the right half of that figure shows what happens if you, in software, are intercepting all of the packets that the VM is generating before they go out to the network card. On the left is an alternative technique called SR-IOV, a single root I/O virtualization, where that same mechanism that allows you to share the device is instead placed into the hardware itself as opposed to being part of the software stack. And doing the approach of SR-IOV can allow you to save a huge number of those host CPU cycles that I mentioned is an important goal, and also can help improve performance and make things also more predictable. So to help give some numbers to this, we ran a few tests here, and we can show that for both 100 byte packets, so some pretty small packets that the host is generating, as well as jumbo packets of 9,000 bytes, the impact of software-based virtualization is rather significant. So the blue in both plots here is the bare metal performance, where you just are generating traffic from the host machine without any virtual machines in between and no virtualization. And that gives you kind of the idea of the roughly maximum possible performance if you're not introducing the overhead of running your VMs. And then the other colors, other than green, are the software-based virtualization methods, and green is the SR-IOV hardware-based virtualization method. And you can clearly see that if you have hardware-based virtualization, the performance keeps up with and is very close to approximately the performance of the bare metal, whereas the software-based approaches have pretty abysmal performance, like potentially like 4x or more slower than the ideal maximum. So to summarize, if you use hardware-based virtualization mechanisms, you are going to have potentially lower latency than the software-based methods, potentially higher throughput, and also lower CPU effort, which is just a bunch of pros. But the problem is that to do this, you need hardware that explicitly supports doing this virtualization, which not all devices support. Moreover, if you were to look at the landscape of what's available in the SmartNIC community, you'll find that none of the open source SmartNICs that you can test and build architectures on top of have really looked at virtualization at all. None of them support SR-IOV or other types of virtualization offload. And there are also a number of other lacking critical features that I'll get to when we go over the third part of this talk. So in this particular project, we started with Corundum, the open source NIC here, and looked at it and then decided to basically investigate the deployment and release an implementation of SR-IOV on top of it, along with a couple other features. But why did we do this? Well, Corundum has a pretty active development community. The design is basically full custom Verilog RTL, so we could explore numerous different implementations for our ideas and come up with the best one. And then also it has support for a huge number of boards and pretty clear documentation as well. So just to summarize kind of what the overall goal here is that there are, like I said, there are a huge number of different projects and ideas that people want to deploy on their network cards. These require you to actually have a SmartNIC to test them on. And the problem is that no open source network cards support any form of hardware virtualization. This results in you getting extremely poor performance in settings where you're trying to test what your deployment would look like in the cloud. So a huge percentage of your overhead, if you're trying to test your idea in a cloud setting, will come just from the fact that you don't support this virtualization, which means that it's rather difficult to evaluate the quality, performance gains, etc. of your design when you're being basically destroyed by something out of your control. And so OS4C, the goal here is to kind of push forward what's available in the open source network card domain so that this problem is alleviated and you can focus on just what your offloads are or your new architectural features are. So the three key contributions of this work were the first open source NIC with support for hardware virtualization. We support a new scheduler that is basically designed with that in mind. So the cloud tenants and cloud providers both have control over certain settings within the scheduler in order to basically specify how they want to distribute bandwidth. And then third, we provide a simulation tool for the system. So this is a high-level block diagram of our architecture. It's based on, like I said, the Corundum NIC. So I've highlighted here kind of which blocks we changed. So the blocks in red were changed to kind of a moderate degree from the original Corundum design, and then the blocks outlined in dark black here were heavily modified in order to support hardware virtualization. So one of the key things that we changed was that, like I said, the point of virtualization is so that multiple people can share access to the hardware, which means you need to ensure that people aren't stepping on each other's toes. We did that by building basically a mechanism very similar to virtual memory within the SmartNIC itself, where all addresses generated by the driver for accessing the NIC are also come along with the particular function ID, which is a designator indicating kind of which tenant, which cloud tenant, which VM, however you want to think about it, is using the device. And by combining both the function ID and the device address, we're able to specify a unique resource that no other tenant has access to. So to make this more concrete, if you look at the bottom left, we essentially divide each type of resource, so here's the queues, into chunks, with each chunk being allocated to a specific function. Then the uppermost bits of the translated address are set by this function ID, which allows you to basically shift down this list of resources and only end up in the pool that is associated with the resources you should have access to. And then the actual device address generated by the driver then selects a subset within that pool of resources that you have access to. And this allows you to essentially use some subset of the total resources of the network card during deployment without the possibility of you reading, modifying, or accessing someone else's data. In addition to like security and making sure you can only access your resources, we also provide a mechanism for virtualizing the performance of the network card, and this is done through our two-stage weighted round-robin scheduler. Essentially, we have two parts to this. I won't go into the details. If you're curious, you can read the paper. One portion is designed for selecting which cloud tenant should have access to the, or should be scheduled next. And then once we've decided which cloud tenant should be scheduled, we then do a second round of scheduling to decide which of the particular queues that contain their packets should be scheduled. So the first step of deciding which cloud tenant allows the cloud provider to essentially divide the bandwidth, divide the network performance among all the cloud tenants how they see fit. The first decision decides basically which percentage of the bandwidth each cloud tenant should get. And then the second stage allows each cloud tenant to specify which of their queues should have the share of that bandwidth that they've been given. And so this allows the cloud tenant to prioritize certain flows that they're running within their virtual machine over other flows. And if you were to look at some kind of results here based on this mechanism for enabling hardware virtualization, you'll see that there are pretty astronomical gains, especially in latency. So on the top here are our latency plots. We plot the bare metal performance of Corundum, basically with no virtualization. What happens if you introduce a software layer of virtualization between the NIC and the VM with Corundum VirtIO, and then we show OS4C performance, and then also compare that to like an industry standard SN1000 FPGA SmartNIC that you could buy. And as you can see, OS4C has 5x gains on 100 byte packets at the 50th percentile, and also huge gains as these percentiles go up towards 99.9. And this holds true both for large and small packets. And then in terms of throughput numbers, we see the same thing where essentially the software-based performance, Corundum VirtIO, is by far the worst throughput on both small and large packets. And then as soon as you introduce hardware-based virtualization, the performance gap between bare metal and the virtualized system drops significantly, especially for large packets. We also see significant gains in terms of CPU cycles required to generate packets. So once again, if you do hardware-based virtualization, it has significantly less CPU cycles per packet than if you're doing software-based virtualization. So essentially, our design is able to dramatically reduce packet latency, improve throughput, and then also reduce the number of CPU cycles you have to spend on processing packets. So in conclusion, we identified that these current open source platforms haven't looked at virtualization at all, and we have remedied that problem by creating the first platform with hardware virtualization support. And so you can focus on the actual things you want to deploy without having to worry about the overheads associated with just the fact that you're running in a virtualized system. Now, there are a number of limitations here. We don't support network virtualization, meaning this is just device virtualization, just making sure people can share their device. We're not doing things like VXLAN or VLAN or other types of overlay networks, etc. The application block virtualization is rather simple, which I'll go into in one moment. And then the big one here is lack of flexibility. So what Greg was talking about earlier was the ability to partially reconfigure your FPGA. So during runtime, changing exactly what the FPGA is doing without having to reboot your entire system. That's something that is lacking from all of these projects and is a key feature of what I'm going to go into right next. So next to go into our work AdaptNIC, which is here, the brief disclaimer, we're still working on it. This is subject to change, but this is kind of the path we're going, and we've gotten pretty far into it. I said just, 5 minutes ago that basically there's two types of projects. There's the platform to facilitate basic research testing, and then there's also the idea of revolutionizing what's capable in SmartNICs. Our former project, OS4C, kind of is in the top camp of just making these platforms more capable, and then the bottom camp here is our next work, AdaptNIC, which will be focused on revolutionizing what's possible in SmartNIC architectures. Just to quickly re-show this, right, we have this on-path NIC where basically all packets are shoved through the same pipeline of offloads. Now, the problem with this is it's actually pretty inflexible. If you're passing all packets through the same path here, this results in you doing uniform, identical processing on every single packet, regardless of the type of packet that's being generated. So for example, if you're running in the cloud and one person's running an AI workload that might want an AI accelerator, and someone else is running something that would require a compression accelerator, you have different requirements, and yet they're being shoved through the same pipeline of offloads. This is clearly a problem because you don't want to actually do all the processing on both of them, and this results in either redundant or unnecessary hardware or extremely complex control logic. Try and get around that. There have been two kind of major works over the last few years that resolve this, or attempt to resolve this at least. The first of these is Panic, which introduces an RTL crossbar, where instead of basically one pipeline of offloads, they have essentially each packet can be set through a subset of the accelerators by going through this RTL crossbar over and over again. And then on the right, we have SuperNIC, which is a more recent work that basically says, okay, instead of having one fixed pipeline, why don't we have a handful of pipelines, essentially, and pass packets through one of that handful of pipelines. Now, the problem with these is primarily that RTL crossbars are not very scalable. If you were to do like a soft logic crossbar on top of your FPGA, you're going to be met with limitations in terms of throughput, clock frequency, and also the number of endpoints you can realistically support. It's really challenging to meet the extremely high throughputs that we're looking at, like 200, 400 gigabit per second, if you're using soft logic to route between a bunch of different stuff on your design. So our architecture leverages the fact that the Versal FPGAs, particularly the V80, comes with a powerful NOC, a network on chip, that will allow us to build our own custom architecture to route between the different accelerators and other parts of the SmartNIC architecture that we've designed. So to kind of step through what our architecture will look like, first we're going to leverage the NOC, like I said, which has up to 800 gigabytes per second of throughput, roughly. And based on our math, should enable us to have around 16 endpoints to connect to our NOC, assuming each endpoint that we want to have here has up to 200 gigabit per second. Depending on your throughput target per tile, per NOC endpoint, you could maybe have more or less, depending on your goal, right? If you're trying to hit 400 gigabit per second on endpoints, then you might be able to have less total NOC endpoints here. The second major feature is that every accelerator, as well as a few other key blocks, are now partially reconfigurable during runtime. This allows you to dynamically, during deployment, depending on what cloud tenants are running on your system, swap out the accelerator that's running to match their needs. And this is leveraged and this leverages and builds on the work that Greg was presenting earlier in the talk. Essentially, during deployment, as cloud's VMs are migrated or closed or opened up, the cloud tenant can specify, hey, I want this functionality to be available to me, and then the cloud provider goes and reprograms a subset of the network card to then support that feature without having to take down the rest of the system. And then third, we're going to provide a few custom example offloads here, including some security and encryption and protocol level offloads, just as an examples during our work. And then another unique feature is that we're offloading all management functionality to an ARM core here. This is on the V80 itself and connected to the NOC. And basically we'll use this for managing all of the different parts of the system and intercepting all control plane operations from the host. And this allows us to completely offload all major hypervisor functionality to the network card itself instead of having it running on the host, which improves security and reduces CPU cycles. We also support quality of service guarantees through a custom distributed scheduler, which I don't have time to get into. And then also, of course, going with the trend that we started with OS4C, we support full virtualization of both the network and device itself. So to summarize, the new NIC we're building here will support up to 16 different kind of tile endpoints, each with up to 200 gigabit per second. This should allow for us to have roughly 12 different large accelerator blocks that can be dynamically reprogrammed individually, which is significantly more than previous state-of-the-art, which only supported up to 8 endpoints at 100 gigabit. So we're supporting twice as many endpoints at twice the throughput compared to previous state-of-the-art. We're going to support full virtualization, which, like I said, none of these new SmartNIC architectures have even looked at. And we will support partial reconfiguration and complete offloading of our control plane to hardware. And we target releasing this sometime next fall. And in conclusion, SmartNICs are increasing in popularity with a ton of papers on different accelerators and offloads. A few works have looked at creating new platforms for NIC research, but they are very limited in their capabilities. OS4C is the first NIC with virtualization support, and AdaptNIC is going to build on that to also support partial reconfiguration, greater scalability and flexibility. Thank you.
All right. Thank you very much, Scott. That was a fantastic presentation. I really appreciate all the detail, especially kind of the overview on the SmartNIC side of things and then where you're going with the AdaptNIC.